Let's continue with our unit over atomic structure and nuclear chemistry. And in this video, we begin the nuclear chemistry section. Have your periodic table available as you watch and take good notes. As the word implies, nuclear chemistry is the study of the structure of the nucleus. So we focus on changes happening in the nuclei of atoms, which contain the protons and the neutrons. Some terms specific to nuclear chemistry. Radioisotopes. Many known isotopes are radioactive. They are isotopes of atoms with unstable nuclei, which means they have too many or too few neutrons. As a result, they undergo radioactive decay. Radioactive decay happens when unstable nuclei naturally break down into smaller elements and emit particles or energy in the form of radiation in order to become more stable. They decay because their nucleus is unstable due to an unfavorable neutron to proton ratio, and the new element formed has a more stable and favorable neutron to proton ratio. In nuclear chemistry, an isotope is referred to as a nuclide and is identified by the number of protons and neutrons in the atom's nucleus. Transuranium elements are elements above atomic number 92, so past uranium on the periodic table. Uranium is over here, so all these elements here and here are transuranium elements. Very few are found in trace amounts in nature, and most were synthesized or man-made in nuclear reactors and particle accelerators. They are extremely unstable, and most exist for infinitely small moments and decay into smaller, stabler atoms. Now let's take a look at nuclear stability. An isotope of an element is considered stable if the nucleus will not spontaneously decay. Elements with atomic numbers 1 through 20, starting with hydrogen and going through to calcium, have at least one nuclide that is very stable. The nucleus has a 1-to-1 ratio of proton to neutron, and one example would be carbon-12 with 6 protons and 6 neutrons, so a 1-to-1 ratio. Elements with atomic numbers 21 to 83, so starting with scandium and going all the way to bismuth at 83, have at least one nuclide that is somewhat stable or metastable. Their nucleus has a 2-to-3 proton to neutron ratio, and one example would be mercury-200, which has 80 protons and 120 neutrons, so a 2-to-3 ratio. Finally, elements with atomic number greater or equal to 84, so starting at polonium, do not have a stable isotope, and they are all unstable and radioactive. The nucleus has a 1 to greater than 2 ratio of protons to neutrons, so some examples would be uranium and plutonium, but anything above or equal to 84 will be unstable. Transmutation is the conversion of an atom of one element to an atom of another element. Transmutations can occur spontaneously in radioactive decay, or they can be induced when high-energy particles are bombarded into the nucleus of an atom. An unstable nucleus decays when its nuclear configuration is not stable. There is an unfavorable proton-to-neutron ratio. That is, it contains too much energy. The decaying nucleus emits energy as particles and rays and transmutates or decays into a more stable, different element. There are many types of decay, and we will look at them in the next slides. First, we have alpha decay. The nucleus ejects an alpha particle, which is a helium nucleus. You do need to be familiar with what an alpha particle looks like. You need to know the symbol, and you need to know that it looks like this. So let's take a look at an example. When uranium-238 decays by alpha decay, it ejects an alpha particle. So we know that an alpha particle, so He4 and 2, will be ejected from the nucleus. Now we need to figure out which new element is also formed in this process. So in order to do that, we have to know that the mass number and the atomic number are conserved on each side of the arrow. So if we start with uranium-238, the mass of uranium-238 is 238. So if we have a mass of 4 here already, the mass of our new nuclide will have to be 234 to get a total of 238. Then I look at the atomic number. I have 92 on the uranium side, and I have a 2 over here on the helium. So in order to conserve the atomic number, I would have to have a 90 down here, because 90 plus 2 gives me 92. Then I go to the periodic table, and I go find the element with atomic number 90, and that is thorium. So I can write thorium over here. Alpha decay usually occurs in large nuclides. Then we have beta minus decay. Beta minus decay happens when a neutron in the original atom decays to form a proton and a high-speed electron. Again, you have to know the symbol for beta minus. You have to know what the particle looks like, and you have to be able to write it. A beta minus particle is a high-speed electron. So let's take a look at an example again. If lead 210 decays by beta minus decay, we know that a high-speed electron or a beta minus particle is ejected. So here it is. Now again, we have to figure out which new element is formed in the process. So we do the same thing. We know that mass number and atomic number are conserved. So if I start with 210 on the left-hand side, I have to have 210 for my new element for the mass to be conserved. And atomic number, I have 82 on this side. So I have to have an 83 over here, because 83 minus 1 gives me 82. Now again, I go to my periodic table, and I find the element with atomic number 83, and that is bismuth. So I know that my new element is bismuth. So in beta minus decay, the neutron is represented in the original element, and the proton is represented in the new element. The overall result is that the nucleus gains a proton and a beta minus or high-speed electron is released. This type of decay happens in neutron-rich nuclides, which means the number of neutrons was bigger than the number of protons, and a neutron becomes a proton. Beta plus decay. This time a proton in the original atom decays to form a neutron and a high-speed positron. So there's the symbol for beta plus decay. This is what the particles look like. You do need to know that. And let's take a look at an example again. Nitrogen 12 decays by beta plus decay. So I know that a beta plus particle is ejected from the nucleus. I have to figure out what new element is formed. So mass is conserved. So over here, I will have a 12, because 12 plus 0 gives me 12. On the bottom for the atomic number, I have a 7 for nitrogen. So I have to have a 6, because 6 plus 1 gives me 7. I go to my periodic table, and I find element with atomic number 6, and that is carbon. So my new element formed is carbon. So the proton this time is represented in the original element, the neutron in the new element, and the overall result is that the nucleus gains a neutron and a beta plus particle or high-speed positron is released. This type of decay occurs in neutron-poor nuclides, which means there are more protons than neutrons, and a proton becomes a neutron. Gamma radiation. Some nuclides undergo gamma emission only, which is very high energy radiation in which no particles are emitted, just energy, and the resulting nuclide is stable. Many alpha and beta decays also release gamma radiation in the process, and gamma radiation, as we said, is pure energy, not a particle, so it does not have a mass, and it will not be represented in the nuclear equation. Gamma radiation sheds excess energy from the nucleus. A radioactive decay series, also called a decay chain, happens when a radioactive isotope continuously decays into smaller and smaller new radioisotopes until eventually a stable isotope is formed. Alpha, beta, and gamma radiation can be emitted during this process. The parent nuclide is the heaviest nuclide and the one with which the decay chain begins. The daughter nuclides are all the smaller nuclides produced throughout this decay. This concludes this video. Come to class prepared with your notes.